Something happened here. Somebody's messing with my three-dimensional space.
That's a weird sentence.
No, that's right.
I'm going to probably eat immediately after class today, and then might not come back for the rest of the week. So that'll be
All right, I think we're ready to roll here. Y'all ready?
ready as I'll ever be.
Okay, so last class we started talking about the cross product, right? We talked about how you can compute that, by hand mechanically.
Yep.
Talked about some of the properties of cross products. And we got to this, this is where I wanted to start, is this property that we have, or theorem that we have for cross product, that the magnitude of the cross product is equal to the magnitude of the two vectors times sine of the angle between them. And then I think we went through this example. We did talk about the cross product being zero means that the cross product being the zero vector means that the two vectors are parallel to one another. All right, so yes.
Did I see that theorem again? I want to write it down.
Which one? This one? Oops, magnitude of u, magnitude of v, sine of the angle between them. So remember in class the other day you had mentioned, is there another definition for the cross product? And I think you were alluding to this. So it's important. This is the magnitude of the cross product, right? So the cross product itself gives you a vector, right? That is orthogonal to the two vectors that you're crossing, right? Using the right-hand rule. This theorem deals with the magnitude of that vector, how long it is. And it gives you a relationship between the length of that vector, the cross product, and how it's related to the lengths of the two vectors, the two other vectors you're crossing. So this is not an alternative definition for the cross product. It is an alternative definition for the magnitude of the cross product. Yeah? All right, so the question of what this magnitude represents, right, has a very good geometric meaning to it. The length of that vector, that when you cross two vectors, that length of that vector you get actually turns out to be the area of the parallelogram formed by those two vectors, which is kind of an amazing thing if you think about it. Where's my vectors? Right? It's saying if you take two vectors, right, let's say we take this one and cross it with this one, then we're going to use the right-hand rule, right? We get this vector that comes out. That vector that comes out has some length to it. The length of that vector is equal to the area of the parallelogram formed by these two vectors. So visually it looks like this. Let me see here. Let me see here. This will work. So what I'm doing here is I'm crossing the red and the black vector together. Okay, so right-hand rule. I cross the red and the black vector together like this. I get this vector that comes out orthogonal to both, this green vector. Now it's off my screen, but imagine that has some length to it, right? The length of that vector is equal to the area of the parallelogram that was formed by those two vectors. Very, very interesting property, wouldn't you say?
Yeah.
Kind of not really expected to have that result, but that is the case. So this becomes a very easy way for us to find areas of triangles in in two-dimensional space, but also three-dimensional space, right? So we're not just limited to those two. Yes?
Couldn't we also then use that as a different way of finding the cross product if we have more knowledge about that shape?
You could find something about the magnitude of the cross product, but not, you couldn't recover the vector from that.
Gotcha.
not straight away. So let's do this example right here. Find the area formed by those. So I believe we may have crossed those two vectors in last class, but let's just go ahead and do it again just to kind of get us warmed up since it was an entire weekend. So find the area of this parallelogram, right, of the area formed by those two vectors. So we got these two vectors sitting in space. We want to know what the area of the parallelogram formed by those is. So all I need to know is the magnitude of the cross product, right? So the area will be equal to the magnitude of the cross product of those two vectors. And remember, the cross product is not commutative in the sense that if you change the order of the cross product, what happens is that the vector comes out the other direction, right? You cross two vectors, you get a vector that comes out. If you cross them the other way, the vector goes out the other side. But we're looking at the magnitude, which won't matter which way we cross them, because the length of the vector coming out this way is going to be the same as the vector length of the vector coming out the bottom. So I'm going to go magnitude of u cross v. If you wanted to, you could do the magnitude of v cross u. All right, let's actually find the cross product over here. So u cross v, the way I'm going to do that, or at least the way that I showed you, is that I like to write the vector down like this, write the other vector down below it, and then my answer when I cross these is going to be a new vector. It's going to have 3 components to it, right? And we get the first component of this vector by covering this up and doing the determinant on that, treating it like a little 2x2 matrix, right? So -9, I'm going to write down -9. Take away, so I did this times this. Take away this times this, so take away -5. And then the middle one we had to remember, this is the one you put the negative sign on, right? Like you're going to change, you're going to do a determinant, but you're going to make the answer switch the sign, right? So I cover up the middle one. I'm going to take 6, 2 times 3, bless you, and subtract from that 5 times 4, which is going to be 20. And then the last component, we cover this one up. 2 times -2 is -2. And then we subtract from that -3 times 4, which is -12. So our result, and I might need someone to grab a calculator. This is going to be, when I put these together, -4. And then put this together, it's going to be -14, but then change it to +14. And then it's going to be 10?
Yeah.
Okay, this right here is u crossed with v, right? It was the u vector, yeah. This is u crossed with v. Any questions on that? I mean, we did that before. Yes? Where, right here?
Yeah.
That's always you.
The one to the left. The -5. That's parentheses. You have a -5.
Where do I have?
It's -9.
This one, -9 minus
Yeah, that's right.
minus -5. So you do this times this,
Okay.
minus this times this.
Oh, no, I said my cross product wrong. Then I was doing addition, not subtraction.
Oh, in all the determinants,
Yeah.
it's always subtraction.
Okay.
All right, so that's our cross product, right? So now we need the magnitude of that. So to do the magnitude of that, it's the square root of the sum of each of the components squared. So this plus this plus this. Whatever that is. I think y'all can get that from there, right? Just square all those things, add them up, and we'll just leave it like that. We won't even get a decimal or anything. We'll just leave it as a root.
Not going to be a 9.
All right, now, let's extend on that idea. This time, I'm going to give you a triangle in 3-dimensional space. I'm giving you the vertices. So I'm giving you the corners of a triangle in 3-dimensional space. So here's my first point. 1, 4, 6. My next point, -2, 5, -1. And my third point, 1, -1, 1. And I have a triangle, right, like this, sitting in space. And what we want to know is, what is the area of that? So the way I'm going to approach this is I'm going to create two vectors from this triangle. Remember, I'm not giving you vectors, right? I'm giving you points. So I'm going to choose to make a vector here that goes from here to here. I'm going to call that U. And then I'm going to make a vector that goes from here to here. I'm going to call that V. And I know that the magnitude of the cross product, right, the magnitude of that cross product will be equal to the area of the parallelogram. I'm just going to put para here, okay? The area of the parallelogram, and I mean by that this parallelogram. Right? That's the parallelogram formed by those two vectors. So the area of the triangle should be half of that. So that'll be the area of the parallelogram. So taking half of the magnitude of the cross product will be equal to the area of the triangle. And I think I'm just going to set this one up. I'm not going to go through all the computations. Really, the only thing I need to really define in order for you to take this the rest of the way is to define what U and V are, right? Just to make sure we have the correct vectors. So let's see, U is the vector that goes from this point to this point. So I'm going to take this coordinate and subtract that one. That should give me -3. And then I'm going to take 5 and take away 4. That's going to be 1. And then -1, take away 6, right? That's going to be -7. Everyone good with that? And then V is the vector that goes from here to here. So I'm going to go this minus that, so we get 0 for the first component. Then -1, take away 4, that's -5. And finally, 1 take away 6, -5. Those are my two vectors. Now I would go and cross them, get that vector, go take the magnitude, take half of it, right? Because that's, you want the area, you don't want the whole parallelogram. Okay? So again, this actually goes back to this idea of, like, if we had walked into class, you know, let's say beginning of the semester, I said, here are 3 points in space, find the area of that triangle. There's a lot of other things you'd probably try if you didn't know about cross products, right? And especially like this theorem. There's a lot of other geometry, you bring in like trig functions and all sorts of other things. So this makes it really simple to find areas of triangles. Yes?
So on like one of the quizzes, if we had something like this, because there's something kind of like this on the quiz. Would you want it? How far would you want us to grind it down? Like,
if I was asking for the area?
Yeah, like if you were to ask for the area, would you want it to be at, you know, the square root? The
square root of some number, unless it's like square root of 100, then you put 10. But
okay.
Otherwise, just leave it as a square root, as the exact answer, as opposed to a decimal.
Okay,
I wouldn't take off if you do the decimal, but I want to see the root part. All right, so take two vectors, right? Take two vectors. Think about the parallelogram, right? We can find the area of that, but what if you have 3 vectors, right? So let's say you have a third vector now, and you get like a 3-dimensional, you've got the parallelogram formed by these two, and then a parallelogram formed by these two. It's like you get this 3-dimensional solid figure, right, which looks like what I have here. I'll spin it around a little bit so you can kind of see it. See the 3 vectors, red, blue, and black? Those 3 vectors, they form this weird sort of box shape, right? And the question is, can we find the volume of that, right? The volume of that. Well, there is a formula for it, just like we know that the magnitude of the cross product gives us the area of the parallelogram. If you are given 3 vectors, u, v, and w, and you want to find the volume of this shape, which is called a parallelepiped. It's a weird name. Parallelepiped. It's like a shoebox, right? When you have a shoebox, that's every angle between all the corners are 90 degrees, right? But if you start like tilting sides over, you get something that's more like this. And you still have in this shape that all sides are parallel to one another, which is why it's called a parallelepiped. And that's just the name for it. I didn't make it up, all right? So if we want to know the volume of that, here's what it is. You cross any two of the vectors. You cross any two, all right? So if I cross two vectors, I'm going to get a what?
A vector.
A vector. You take that vector and you dot it with the third vector, and that will give you a number, right? Because when you take the dot product to two vectors, you get a number. And then you take the magnitude of that number, which basically means if it was negative, just make it positive. And that will give you the volume of the parallelepiped.
Oh.
All right? We're not going to get into the details of that. You're just going to take that on faith. I believe this is going to maybe help a little bit on the take-home, right? So the order here doesn't matter. I think I do ask us to do this one. Do we want to go through all the work on this? Yeah, go through it? Okay. So let's take a look at trying to find the volume of the parallelepiped formed by those three vectors. So let me go ahead, and notice I'm giving you vectors, right? I'm not giving you like 3 points in space. This is vectors. So I'm going to choose to label this one U, this one V, and this one W. So the volume, by the definition I gave you, is the magnitude or absolute value. It doesn't matter what order I do this in. U dotted with V crossed with W. Did I say it's called the triple product? I feel like I left that out.
You said that.
I don't think I said it. It's called the triple product. All right, so that's what I'm going to do. So that means I want to do the absolute value of the U vector, 1, 4, 6, dotted with the V vector, -2, 5, -1, crossed with the W vector, 1, -1, 1. And then after I do that cross product, I'll have to dot it. So that's the actual, everything plugged in. So what should I do now? Go do the cross, right? Let's go do the cross. I'll do it over here. See if I can squeeze this in over here. So I'm going to take my -2, 5, -1. I'm going to cross it with the 1, -1, 1. That's going to give me a result over here. So let's see if I can move through this. Cover this up. 5, take away 1, 4. Right? That's my determinant. 5, take away the product of those two. So 5 minus 1 is 4. All right, the next one, I'm going to have a negative in front. Cover this one up. I have -2, take away -1, which is the same as -2 plus 1, which is -1. But I have a negative in front of it still, right? Am I going too fast through that, or is that all right with everyone? No. It's okay? Sure? Everyone's good? All right, now cover up the last one. I'm taking these two, that's 2, and then I'm taking away these two multiplied 2, take away 5, -3. So my cross product I'm ready to put in here is 1, 4, 6, dotted with my triple product. I'm sorry, I said that wrong. My triple product is the absolute value of 1, 4, 6, that vector, dotted now with that cross product, which is 4, 1, -3. And the dot products, we missed the dot products. The dot products are easy to compute, right, compared to the cross. So you just multiply this times this, that's 4, plus, now you do this times this, that's 4 again, and then plus you do this times this, that's -18. So I'm subtracting and adding a negative. So 8, take away 18, -10. Absolute value of -10 is 10. That's it. So if you were to take those three vectors, do the triple product, the volume of that parallelepiped would be 10 units, whatever the units are measured in, right? All right, anything else there? All right, last idea of this section, and we can finally move into the interesting stuff that probably a lot of you have not seen before, some new stuff. Torque. So this is just one particular application of the cross product. So in physics, I know a lot of you have taken or are taking physics. This idea of torque is applicable to like when you're tightening a bolt. Right, now normally bolts are threaded what we call the right hand thread, which means when you go to the right it tightens, right? When you go to the left it loosens, righty tighty, lefty loosey. Have y'all heard that before? That's called right hand threads. All bolts don't work that way though, right? There are some bolts that are threaded left hand where left is tight and right is loose. Anyone know where you might see something like that? You don't want it backing off like there's some rotation involved that would maybe loosen it. Bicycle pedals. If you look at like bicycle pedals, if you want to replace your pedals, one side of them is right hand thread, the other one is left. I'll let you think about which one is which. Right, as you pedal, which one would loosen if it was right hand. Think about it. The point is, this is based upon the idea that right is tight and left is loose, right? So we say that torque, all right, torque, this idea of torque, is a vector which represents the tendency of the bolt to turn. Torque is defined to be T or tau, whatever you want to use here with a vector. It's a vector. It's just the cross product of R and F, where R is the position vector of the rigid body, so that would be like the wrench that you're turning. That right there is a vector. And then you have the F, which is the actual force that's acting on that wrench. So if you take those two vectors and cross them, you get the torque. Now, we use the right-hand rule, and then remember that the magnitude of the torque would just be the magnitude of the cross product, which we know from that formula is just the magnitude of R times magnitude of F times sine of the angle between them. So I just have a little animation right here that shows you, like, let's say that we had a wrench, right? And we're going to turn this bolt like this. Okay, so my bolt's right here. We're going to turn it, right, which is going to tighten it. And then the red vector is the force I'm acting on it with. So it's like I'm grabbing this wrench and I'm pulling in this direction, which is kind of weird. You wouldn't want to do that. But if I do that, if I start pulling down like this, it's going to want to turn this, right? And the torque is a measurement of that. Yes?
So the R and F are interchangeable.
They are you saying they are or not? How do you mean interchangeable?
Like you can do F.
Okay, so if you reverse the order of the cross product, that'll give you a vector in the other direction, right? So no, you can't. Now, if you're talking about magnitude of the torque, it won't matter. But if you're talking about the torque vector itself, the order does matter.
That was something my professor was really stingy on. It's like the R always comes before the F.
Yes.
I never understood that.
We can see, it's because of the right-hand rule. Let's take a look over here at this picture. So this picture, oh, why is that moving like that? I don't want that. I want to rotate that. Oops, that's not working. Okay, let me do this. I don't think I'm going to be able to rotate that, unfortunately. So can y'all kind of see this? This picture is this picture in three-dimensional space. So you have the wrench sticking out, and then the force is acting this way. And then do y'all see the blue vector? That's the torque vector. And so do you see that torque vector is going down like that? So here, if I were to do this, take this wrench, pull down with the force right here, it would want to turn it like this, and then the torque would go into the page, right? That would go into the page, which here means down, right? So now, let me take this torque, this force, and again, if I do this, look, I'm having the computer measure the torque, the magnitude of the torque here. Do y'all see that when I am orthogonal, when my R and F are orthogonal to one another, do you see how big the torque is? Mm-hmm. And then when I move that force just a little bit off orthogonal, do you see that the torque gets smaller? Mm-hmm. Right? That's because of this property right here. That this right here, the biggest sine can ever be is 1, and that happens at pi over 2 or 90 degrees. So the biggest torque you're ever going to get, or the biggest cross product you will ever get, is when the two vectors are orthogonal to one another. Which is why when you pull on a wrench, you want to be, when you turn a wrench, you want to be perpendicular to it to get the most torque. Now, of course, if I pull on the end of it, then I should be fired, right? I should not be working at this right? Because you're trying to turn it and you're pulling off the side. Well, look at that. What's the angle between those two vectors? 0, and then sine of 0 is 0, and then you have no torque, right? And then if I go and I turn the vector, the force vector up, now look what happens. Look at my torque vector. It's no longer going down, right? Not into the page, but coming out of the page. Okay, so that's just showing you that there's a connection between, we can take this idea of vectors and cross products and extend them into other subjects, right? You have to remember at the end of the day, you're in a math class, right? So we're not really here to do the engineering problems, the computer science problems. We're here to lay out the mechanical parts of the math, and then you go apply those to other things. All right, that's it. We're ready to move into 10.5 or 10-5. Lines and planes. So before I get into this, let's all agree on something. To define a line right now in this class, to define a line, you need what? 2 points. Is there anything else that you could have other than 2 points? A direction. Think back to college algebra. If you have 2 points, right? Think about this. If I have 2 points, I can define a line between those 2 points, right? As long as those points are distinct points. So you give me 2 points, I should be able to find the line. I could give you the slope and 1 point. It doesn't have to be the y-intercept. It could be any point. Y-intercept would satisfy it, but just the slope and 1 point would work as well. Right? So give me 1 point, and then give me the slope of the line, and I should be able to draw you the line, right? So those are the 2 conditions we need right now to come up with the equation of a line. 2 points or a point and a slope. We're good? All right. What does the equation of a line look like in college algebra? So we define it as a function. We can use f of x, but before that, didn't we do this something like y equals mx plus b? Right? That's like the generic equation of a line in college algebra. This has no vectors in it, right? This is just a nice, simple, linear relationship between x and y. What this lacks for us, what it does not let us do, is define lines in 3-dimensional space. So we need a way of defining a line in 3-dimensional space. We already are covered in 2, right? We've got 2 down, but we need something that extends to 3-dimensional space, even 4, 5, 6-dimensional space. We need some other definition. So that's what this is about. We're going to establish a new definition for lines that will involve vectors, but will allow us to work in any space we want. 2D, 3D, 4D, whatever we want. All right? All right, so we need to first talk about this first step, preliminary concept. It says here I'm going to do this in class, so let me move this so you can see what I'm about to do. It says given 2 vectors I'm going to say this, R0 and R1. Okay, given 2 vectors R0 and R1, let's compute R1 minus R0. So I'm going to draw this. If this is the vector R0, and let me do another vector over here. I'll do it in a different color. Let's say that this is the vector R1. Right? Now these are vectors, so I just put them wherever I wanted, right? I want us to look at this. What is R1 take away R0? There's a bunch of different ways you can visualize this. Here's the way I'm going to do it for you. This is the same as R1 plus negative R0. Right? Wouldn't that be the same? Subtracting 2 vectors is the same as adding the vector that points in the opposite direction. Right? Taking R1, subtracting R0, same as taking R1, adding to it the negative of R0. So visually on this, I'm going to draw negative R0. Right? The negative of R0 would have the same length. It would just point in the opposite direction, yes? How do you add 2 vectors? How do we add them? Like in terms, I know it's like add the first components, add the second, but I'm saying visually, how do we add two vectors together? What do we do? Tip to tail, tail to tip, right? You just need to take the tip of one, add it to the tail of the other. Or paste it to the tail of the other. So what I'm going to do is I'm going to leave R1 here. Okay, I'm going to leave it right there. I'm going to take negative R naught, and I'm going to slide it over, right? Move it wherever I want, up, down, left, or right, so that it is attached to, sorry if that's not exact, that doesn't look perfect to you. Right? So this is R1, and I'm adding to it the negative of R naught, yes? Mm-hmm. And now, the resultant vector is this vector right here. That's where you wind up. So this blue vector is the same as R1 take away R naught. And I'm asking you in here to notice something. If we're given two vectors, R naught and R1, if we compute the difference between the two, the resultant vector is equivalent to the vector from the tip of R naught, right? From the tip of R naught, where's R naught? Right, let me draw. I think I'm going to have to do this separately. So I'm trying to get you to see right now that this vector right here, that vector right there, is the same as the vector that would go from the tip of R naught to the tip of R1. So forget that for a minute. I'm going to put R naught here. And R1 is the black vector right there. I'm going to move it right here, like that. I put them together. Do you agree that this vector I circled in green, do you agree that that is the same as the vector that goes from there to there? Yes? That's what I'm trying to get you to take away from this. Is that if you subtract two vectors, what you create is a new vector that goes from the tip of the one that you're subtracting from the other one. I'm going to see if you understand this by giving you a whole new example, all right? Let's say I take this vector, call that vector u, and then let's take this vector right here. Let's call that vector v. I'm using u and v instead of r naught and r1 just to see if I can kind of confuse you. The vector u minus v should be the vector that goes from where to where on here? Go ahead.
Tip of u to the tip of v.
Tip of u to tip of v. What's the other? Does anyone have a different one, or y'all agree with that? Is it the other way, or is it this way? So look at what I say here. Given two vectors, r0 and r0 and r1, if we do r1 minus r0, so let's do u minus